If you have ever lived with a cat, you know their peculiar talent for climbing into precarious places. Perched on windowsills, balanced on the edge of bookshelves, or exploring the rafters of an old barn, cats seem fearless in their pursuit of height. But for every leap that lands gracefully, there is an occasional misstep. A paw slips, a tail twitches the wrong way, and suddenly gravity takes over. The sight of a falling cat is terrifying. Yet, to the astonishment of countless witnesses, these animals often land not in a crumpled heap, but on their 4 feet, shaken but remarkably unhurt. This uncanny ability has fascinated people for centuries. How does an animal that might fall upside down from a high shelf manage, in a brief arc of descent, to rotate its body and align its legs with the ground? Dogs cannot do it. Humans certainly cannot. Even monkeys, with their agility, do not replicate this same trick in midair. Cats alone seem to possess a built-in safety mechanism against falls, one that borders on the miraculous. The phenomenon is so consistent that it has become part of our cultural shorthand. To say that someone lands on their feet is to suggest resilience, resourcefulness, and perhaps a touch of feline magic. But for scientists, the explanation is not magic at all. It is physics, biology, and evolution woven into a reflex so precise that it has earned its own technical name, the righting reflex. The righting reflex is the automatic ability of a cat to orient its body during a fall so that it lands feet first. Unlike a learned behavior, it is instinctive, present even in kittens just a few weeks old. The reflex is triggered the moment a cat senses a loss of balance. Within fractions of a second, its nervous system calculates how to twist its body, redistribute mass, and prepare its limbs for impact. What seems like a blur of fur and motion to human eyes is, in fact, a finely tuned maneuver honed by millions of years of evolution. But for much of history, this remained a mystery. Observers could watch cats fall and land upright, but they could not see what happened in the space between. The fall was too quick, the motion too subtle. It was only with the advent of modern science, and particularly with the invention of high-speed photography in the late 19th century, that the secret could be captured, slowed down, and studied frame by frame. One of the earliest breakthroughs came from the French scientist Etienne Jules Méry, who in 1894 used chronophotography to record the mid-air twist of a falling cat. His photographs, published in scientific journals, were both revelatory and controversial. They showed, undeniably, that the cat did not push off from anything. It seemed to violate the conservation of angular momentum, one of the bedrock laws of physics. How could the cat rotate in free fall without external forces? Mary's images sparked a debate that drew in physicists, biologists, and skeptics alike. The puzzle became known as the falling cat problem, and it occupied some of the sharpest minds of the era. For scientists, explaining the righting reflex was not simply about cats. It was about the fundamentals of motion itself. If cats could rotate in midair without breaking physical laws, then there must be a subtle mechanism hidden within their bodies that allowed it. Unlocking that mechanism would deepen our understanding of biomechanics, inertia, and the interaction between living systems and physical laws. At the same time, veterinarians and animal lovers saw practical importance. In urban environments where cats lived alongside tall buildings, falls were not uncommon. Understanding how cats survive these tumbles could offer insights into injury prevention, not only for pets, but potentially for humans as well. By the early 20th century, newspapers were already reporting extraordinary cases of cats falling from multiple stories and walking away with only minor injuries. The stories fueled the mystique and the scientific urgency alike. As we will see, the riding reflex combines anatomy, neurobiology, and physics in a way that borders on artistry. It is a dance of the spine, the vestibular system of the inner ear, the positioning of the limbs, and the counterweight of the tail. Piece by piece, scientists unraveled the sequence. Head turns first, spine follows, legs extend, tail adjusts. Each stage conserves momentum even as it transfers rotational energy from one part of the body to another. The elegance of this reflex has since inspired engineers designing robots that can reorient themselves midair, astronauts training to move in zero gravity, and physicists exploring the limits of rotational mechanics. Yet it all began with the simple observation of a household pet taking a fall and emerging improbably on its feet. In the sections that follow, we will trace the story of how cats achieve this feat, from the earliest experiments to the cutting-edge science of today, and discover what this furry acrobat can teach us about the laws that govern life and motion. The year was 1894, when Etienne Jules Méry, a French physiologist fascinated by movement, published a series of photographic plates that would bewilder scientists for decades. Using his chronophotographic gun, a device that could take a rapid sequence of images on the same frame, Méry captured a cat dropped upside down in freefall. In the frozen snapshots, the cat rotated with a grace that no one had fully appreciated before. By the final frame, all four paws were neatly aligned with the ground. The implications were immediate and puzzling. Mary's images seemed to show that the cat rotated without pushing off from any surface. In physics, such a movement should have been impossible. According to the principle of conservation of angular momentum, an object in freefall cannot change its orientation unless acted upon by an external torque. A spinning ice skater can speed up by pulling in their arms, but they cannot change the fact that they are already spinning. How? Then, could a cat that started with zero angular momentum suddenly twist itself upright in midair? The paradox became known as the falling cat problem. It was not merely a curiosity for feline enthusiasts. It was a genuine scientific riddle. For decades, physicists, biologists, and mathematicians debated possible solutions. Some accused Méry of trickery, suggesting he had dropped the cat onto a hidden platform. Others speculated that cats had some special exemption from the laws of physics. Eventually, the explanation emerged from closer observation and more refined mathematics. The cat was not, in fact, violating angular momentum. Instead, it was exploiting the flexibility of its body in ways that most other animals cannot. The solution lay in the mechanics of segmented rotation. A cat's body can be thought of as two main sections, the front half and the back half. By twisting these sections in opposite directions, the cat conserves angular momentum overall, but still manages to rotate each half relative to the other. First, the head and front legs rotate in one direction while the hindquarters counter-rotate in the other. Then, as the spine bends and straightens, the process reverses, with each segment trading angular momentum back and forth. In this way, the cat as a whole remains in compliance with physics, even as it performs what looks like an impossible maneuver. High-speed photography confirmed this. By the mid-20th century, scientists could capture thousands of frames per second, revealing that the riding reflex occurred in a precise sequence. Head initiation. The cat first orients its head, guided by the vestibular system in the inner ear, which provides a sense of balance and spatial orientation. Spinal twist. The front half of the body rotates, while the back half counter-rotates, maintaining conservation of momentum. Rear alignment. The hind legs follow, aligning with the already rotated front legs. Final preparation. All four legs extend, absorbing shock upon impact, while the tail may act as a stabilizer. This process takes only a fraction of a second, often less than half the time of the fall itself. Kittens begin developing the reflex at around 3 to 4 weeks of age, and by 6 to 7 weeks, it is nearly perfect. Unlike behaviors that must be taught, the riding reflex is hardwired into the cat's nervous system, an evolutionary gift of survival. The fascination did not end with Mary. Throughout the 20th century, the riding reflex became a topic of study not only for animal physiologists, but also for aerospace engineers. During the early years of the space race, scientists at NASA conducted experiments with cats to better understand how organisms might move in weightless environments. After all, astronauts would soon be tumbling in zero gravity, where the ability to reorient one's body without external surfaces would be crucial. Cats, it turned out, were natural experts in exactly that challenge. From a biomechanical standpoint, the riding reflex illustrates one of the most elegant solutions to the problem of falling. Cats are uniquely equipped for it. Their spines are extraordinarily flexible, allowing a wide range of twisting. Their inner ear vestibular system is highly sensitive, giving them rapid feedback on orientation. Their relatively low body mass and loose skin reduce the impact of sudden rotations. Their tail functions as a counterweight, helping to fine-tune balance. Though interestingly, even tailless cats, like the Manx breed, can land on their feet. And yet, not every fall ends harmlessly. Veterinarians in large cities, such as New York, began to notice a peculiar phenomenon in the 1970s, which came to be called high-rise syndrome. Cats falling from greater heights sometimes survived with surprisingly minor injuries, whereas falls from shorter distances could prove more dangerous. The counterintuitive reason lies in terminal velocity. After a certain height, a falling cat reaches maximum speed and has enough time to fully orient itself, spread out its limbs, and create drag, like a parachutist, which slows descent. At lower heights, the cat may not complete the full riding sequence before impact, leading to greater injuries. This revelation turned the riding reflex from a curiosity into a survival mechanism with measurable outcomes. In one widely cited veterinary study, cats falling from as high as 32 stories had survival rates exceeding 90%, provided they received prompt medical care. While not every fall is without harm, the combination of the riding reflex, low terminal velocity, and shock-absorbing limbs makes cats remarkably resilient against the perils of gravity. The falling cat problem may have begun as a physics paradox, but its resolution expanded far beyond. By examining how cats solve the puzzle of freefall, scientists deepened their understanding of angular momentum, biomechanics, and even spaceflight dynamics. And in doing so, they revealed a hidden truth. What looks like magic is often nature's cleverest engineering. To understand the riding reflex in its full depth, we have to step squarely into the domain of physics. While biology gives cats the anatomical tools, a flexible spine, sharp reflexes, and balance sensors, it is physics that explains how those tools are used. The challenge, as scientists once puzzled over, is angular momentum. This principle, central to mechanics, states that a system's total angular momentum remains constant unless acted on by an outside torque. In simple terms, you cannot start spinning out of nowhere. An ice skater pulling in their arms spins faster, but they are not creating new spin. They are redistributing what they already had. The paradox of the falling cat is that it appears to begin with zero spin and ends up rotated upright. The resolution lies in the cat's segmented body. Imagine the animal as two cylinders connected by a hinge, the front half and the rear half. By curling its spine and adjusting its legs, the cat manipulates its moment of inertia, essentially its resistance to rotation. Here's how it works. The cat tucks in its front legs and stretches out its back legs, lowering inertia in the front and raising it in the rear. This allows the front half to rotate quickly while the back half rotates more slowly in the opposite direction. The cat then reverses the process, extending the front legs and tucking the rear. Each switch transfers rotational momentum back and forth, but overall angular momentum remains conserved. Through this sequence, the cat rotates its body without violating physics, and all without any external push. In effect, the cat is performing an intricate dance with momentum, trading it between body sections like partners in a waltz until its orientation matches the ground. The tail, often thought of as essential, is actually optional. Cats with long tails use them to fine-tune balance, but even tailless cats succeed in righting themselves. The main driver is the flexible spine and coordinated limb movement. What makes this ability so astonishing is the speed and precision with which it happens. Studies show that a cat can complete the righting reflex in as little as 1/8 of a second. In many cases, the fall itself may last only a second or two. Yet within that window, the nervous system must sense imbalance, calculate adjustments, and execute the full twist. Humans, by comparison, are sluggish in midair, with no built-in reflex to save us. This precision has not only fascinated biologists, but inspired engineers and roboticists. The cat's righting reflex is often cited in research on self-righting robots. Machines that can recover from being flipped, whether disaster response robots, drones, or even exploratory rovers, borrow ideas from the feline strategy of redistributing mass and manipulating inertia. By studying cats, scientists gain blueprints for designing robots that can recover autonomously when disoriented. Astronautics, too, has learned from cats. In zero gravity, the challenge of orienting the body without external surfaces mirrors the paradox of the falling cat. NASA's interest in feline righting during the early space program was not whimsical. It offered practical insight. Astronauts drifting weightless in space could apply similar principles. By moving one part of the body one way and another part the opposite way, orientation could be changed without violating momentum. Cats, in essence, were performing a low-gravity trick long before humans left Earth. There's also a lesson in resilience. The so-called cat parachute effect, spreading their limbs wide to slow descent, shows how adaptation goes beyond physics alone. A cat that has time to fully extend its legs and body creates drag, lowering terminal velocity. For humans, skydivers do much the same. Spread arms and legs to stabilize and reduce speed. The parallel is striking, reminding us that the survival strategies of animals often echo in our own technologies. Still, the righting reflex is not infallible. Veterinarians note that improper landings can cause injuries, especially in falls from moderate heights, where the cat cannot fully extend its limbs before impact. The so-called high-rise syndrome continues to be a reminder that while cats are resilient, they are not invincible. What the reflex does provide is a significant evolutionary advantage. In the natural world of trees and cliffs, where felines evolve as hunters and climbers, the ability to land on one's feet could mean the difference between survival and death. Thus, the falling cat is more than a curiosity. It is a symbol of the deep interplay between biology and physics. Evolution provided the blueprint, but physics is the stage on which the performance unfolds. To watch a cat twist in midair is to see Newtonian mechanics and Darwinian adaptation fused into a seamless act of survival. The falling cat problem, once a paradox of physics and a curiosity of pet owners, has evolved into a window on broader truths. At its heart, the riding reflex is a survival adaptation, sculpted by natural selection over millions of years. But for us, watching and studying, it has illuminated aspects of balance, momentum, resilience, and even our relationship with animals. Evolutionary perspective, why did cats evolve this ability while most animals did not? The answer lies in their ecological niche. Cats are arboreal hunters by ancestry. Even domestic cats, curled on couches today, descend from wild felines that spent much of their lives climbing, leaping, and stalking prey among trees and cliffs. For such creatures, the risk of falling was ever present. An animal unable to recover from a slip might not survive to hunt another day. Over generations, cats developed the anatomy and reflexes that granted them this remarkable edge. Their spines became exceptionally flexible, their vestibular systems highly tuned, their musculature adapted for quick response. The riding reflex, therefore, is not a party trick but an evolutionary safeguard. It represents the silent wisdom of countless ancestors who survived because they could land on their feet. Cultural fascination humans, of course, have not merely studied cats scientifically. We have woven their abilities into myth and metaphor. The saying that a cat has 9 lives springs in part from the observation that they often emerge unscathed from falls that would devastate other creatures. In folklore, cats are portrayed as mystical beings, defying gravity and death alike. In modern culture, viral videos of cats tumbling from counters or balconies and then walking away unharmed circulate endlessly. While often humorous, they echo the same astonishment felt by 19th century scientists. The difference today is that we can explain the phenomenon, even if it remains no less awe-inspiring. Veterinary science and reality, it is important, though, to separate myth from fact. The riding reflex increases the chances of survival, but it does not guarantee safety. Veterinary studies show that cats can suffer fractures, internal injuries, or worse from falls, especially if the fall height is insufficient for the full reflex to unfold. Ironically, higher falls sometimes result in fewer injuries because cats reach terminal velocity, relax their bodies, and distribute impact more evenly. This paradoxical pattern, called high-rise syndrome, became particularly evident in the late 20th century as urbanization increased. Veterinarians in cities reported numerous cases of cats surviving falls from 10, 20, or even 30 stories. Their resilience, while remarkable, should not encourage complacency. Responsible owners must recognize that windows, balconies, and tall furniture still pose risks. The riding reflex is extraordinary but not invincible. Modern applications beyond veterinary medicine. The study of cats has rippled into surprising fields. Robotics researchers continue to draw inspiration from feline mechanics, designing machines that can reorient in midair or recover from disorienting tumbles. Small drones, for instance, may use algorithms modeled on the cat's redistribution of mass to stabilize themselves after collisions. In space science, lessons from the falling cat inform astronaut training. In microgravity, astronauts must learn to reorient without pushing against surfaces. The segmented body technique that cats employ offers a biological analog. It is not difficult to imagine that when an astronaut twists their torso one way and their legs the other to rotate in a space station, they're echoing the same physics that has saved countless cats on Earth. Even biomechanics for human safety has gained insights. Parachutists and gymnasts practice body control strategies that resonate with feline maneuvers. The core principle: altering distribution of mass and inertia to change orientation, links disciplines as diverse as animal biology, sports science, and aerospace engineering. The broader lesson, perhaps what is most compelling about the riding reflex, is not only what it tells us about cats, but what it reminds us about nature. The laws of physics are universal and uncompromising. Yet within those laws, life evolves ingenious solutions. The cat cannot suspend the rule of angular momentum, but it can bend within it, exploiting flexibility and timing to turn inevitability into opportunity. This is why, more than a century after Mary's photographs, the falling cat remains an enduring image. It is a symbol of adaptation, resilience, and grace under pressure. Scientists still cite it in textbooks as a case study in angular momentum. Engineers still look to it for design ideas. Pet owners still marvel at it in living rooms and backyards. And so, when we watch a cat leap from a windowsill, miss its mark, and tumble, only to twist, extend, and land upright, we are not merely witnessing a survival reflex. We are watching a live demonstration of physics perfected by evolution, performed by one of humanity's oldest companions. The story of the fallen cat, then, is not just about animals. It is about the unity of natural law and living ingenuity. It is about how a creature no larger than a loaf of bread embodies principles that extend to astronauts in orbit and robots on Mars. It is about how something that once seemed magical turns out, under the lens of science, to be even more wondrous, a choreography of motion, balance, and life itself.